Hi everyone, I am Sharath. Today our group is presenting a complete hybrid feature engineering pipeline for classifying skin lesion images from the HAM 10,000 dataset. We are a group of four, each member performed different tasks, and Sri Pradhan handles exploratory data analysis and extracted the discrete wavelet transform texture features. Ashita performed all pre-processing steps including construct limited adaptive histogram equalization, gamma correction, and extracted illumination based features. Akshay extracted the local binary patterns and Laplacian variance features for texture and sharpness analysis. And I worked on deep feature extraction using ResNet 50, feature fusion, and conducted all the experimental evaluations. Our position in the project is that hybrid feature fusion is more reliable than using only deep learning or only handcraft features. You can see our position here, and we apply simple ethical and analysis framework focused on accuracy, fairness, and generalization. Following beneficiency and non-maleficiency, we avoid misleading and oversampling and ensure that pipeline reduces misclassification risk. We also follow ACM professional ethics by being transparent, pre-processing data responsibly, and evaluating performance fairly across all classes. You can see the ethical framework, the principle of beneficiency and non-maleficence, and ACM code. And coming to the data set, we used HAM 10,000 dataset, which is publicly available in Kaggle. It consists 10,015 images across 7 skin lesion types. It's highly imbalanced with it's highly imbalanced. You can see in the code. It's highly imbalanced across the various classes, and NV present the highest samples. And to address these challenges, we applied contrast limited adaptive histogram equalization and gamma correction to normalize brightness and enhance lesion structures as each image is in a different brightness levels. Within the dataset is ready, we now move into our complete code pipeline to show how we solved these issues step by step. From here on, Sri Pradhan will continue.
Hello all. From here, we begin the pipeline by importing the necessary libraries and loading the metadata and image paths into a data frame. After loading, we perform basic EDA where we immediately observe the class, imbalance, and variation in image sizes. Next, we analyze the pixel intensity distribution before and after pre-processing. We can see that after processing, it clearly improves the contrast. After pre-processing, we move into feature extraction and apply all 5 handcrafted and deep feature methods. Illumination features give us brightness and contrast information. DWT captures multiscalar textures. LBP extracts micro patterns, and Laplacian variance measures border sharpness. Each of these is useful because skin lesion classes differ in texture, structure, and edge intensity. Then we extract deep features using ResNet 50, which captures high-level lesion patterns that handcrafted descriptors cannot. Combining handcrafted features with deep embeddings gives us a complete representation of very lesion, covering both low-level detail and global structure. Once all features extracted, we store them in perq files and match them into a single hybrid feature matrix. From pre-processing, we extract 3 illumination features: mean, standard deviation, and contrast, to capture global brightness variations. The DWT module contributes 8 features summarizing low frequency structure and horizontal, vertical, and diagonal edge patterns. LBP produces 10 histogram bins, then capture micro texture, and then Laplacian adds 1 sharpness feature to measure border clarity. Finally, the deep model ResNet 50 extracts a 2040 dimensional embedding, give us a rich semantic representation of each lesion. Together, these handcrafted and deep features create a hybrid vector that combines illumination, texture, sharpness, and high-level patterns for stronger classification performance. With the fused dataset ready, we split the data into training and testing sets and being evaluating different classification models. So from here, Ashwita will explain what all experiments we did in this project.
Yeah, hello everyone. Now, if we move to the experiments that we've performed using this fused data set, we tested multiple configurations like hybrid raw, handicraft only, deep only, hybrid with class weights, hybrid with SMOT, and finally hybrid with PCA. We did all this to understand the contribution of each feature set and each balancing strategy. For every setup, we trained SVM, XGBoost, and Random Forest to compare the model performance. So, in the hybrid raw experiment, we saw that the XGBoost achieved the highest accuracy, while the SVM gave the best macro F1, showing it handled the imbalance more effectively. Now, the ROC curves for the hybrid SVM displayed that the strong class separability, confirming that the fusing handcrafted and deep features significantly strengthens the representation. Now, when we tested the handcrafted only features, here the accuracy and F1 dropped compared to the hybrid results, but the sharp plot revealed that LBP and DWT features were still meaningful. This showed that the texture and the illumination information were useful, but not sufficient alone without higher level patterns. So deep only results naturally improved and the performance because the ResNet 50 embeddings capture the structure and rich semantic structure. However, even with these strong deep features, hybrid fusion will still outperform them in the macro F1, proving that the handcrafted features add valuable low-level information the deep network sometimes misses or fades. So next, by applying the class weights that produce the most stable and the balanced results across all the classes. Hybrid class weighted XD boost and the hybrid class weighted SVM gave the best overall combination of accuracy and macro F1. The ROC curves under this class weighting were the cleanest and most consistent among all the experiments that we have conducted on our data set. Next, the Akshay will continue.
The SHAP summary plot shows that the handcrafted features like LVP histogram bits, illumination, mean slash contrast, and DWT coefficients appear among the top influential features alongside deep embeddings. This confirms that low-level texture and illumination cues meaningfully support the deep features and strengthen the classifier's decision making. We also tested SMOT compare balancing methods. In our case, SMOT not only increased the minority class counts, but also improved macro F1, giving a best overall model. The hybrid SVM with SMOT achieved a macro F1 around 0.60 and strong outcomes. So in this data set, the SMOT-based hybrid SVM became a top performing configuration. Finally, PCA helped reduce dimensionality and still maintain stable performance, showing the hybrid features carry strong structure even with contrast. SVM, PCA, and class weights maintain balanced results, demonstrating the flexibility of the fused feature set. Across all experiments, the overall pattern was consistent. Hybrid fusion with SMOD delivered the strongest macro F performance, reaching around 0.60 with SVM. Deep features alone performed well but were less balanced, while handcrafted features added valuable texture and illumination cues that strengthened the fused representation. These results validate our position that combining multiple feature families with smooth balancing produces a more reliable and generalizable classifier for all 7 lesion types. To conclude, our hybrid feature engineering pipeline successfully addresses the challenge in the HAM 10,000 dataset by improving preprocessing, capturing diverse feature types, and using realistic balancing strategies. Compared to previous works that focused on single feature approaches or aggressive oversampling, our pipeline delivers stronger generalization and more stable performance across all 7 lesion classes. This is the end of our presentation.
Thank you.